second midterm practice exam, problem 6. Find the potential V everywhere inside this situation where we have a square of size A and 2 of the walls are at potential minus V naught and 2 of the walls are at potential plus V naught. And so here is a side-on picture of that, and we're interested in finding the potential here in the interior, right? That's what we want to do. So to do this, I'm going to use the same trick that we used in the in-class example problem, right? Where I'm going to write our full problem. Okay, I'm going to break this apart into 2 pieces. I'm going to say that this can be written, right? We're going to use the superposition principle and say this can be written as looking only at something with 2 sides at positive V naught, and only, and then add that, sorry, to the 2 sides at negative V naught. And furthermore, I'm going to flip this so that I have the same type of problem. So I'm rotating this such that the 2 sides of negative V naught are on the side. And so I can label this. This might be V total. Okay, this might be V1, and this might be V2. Now, one of the beautiful things I have right away, right, is I can see through symmetry here that if I have positive V naught on these 2 sides or negative V naught on these 2 sides, it's the same problem with just a minus sign switched. And so V2, V1 is equal to minus V2. And so we only have to solve for one of these. I don't have to solve for both of them, I only have to solve for one of them. And then we're going to use the trick in the end, right, that this V total is going to be equal to the V1 of x and y plus a rotated V2 of y and x, where here I have to be careful about the rotation because it depends on where I put my origin. If my origin's right in the center, it's exactly like I said that, but if my origin's off here, I have to do some work. Okay, so let's look specifically for V1. We're trying to now solve for V1, so let's write down the problem. The problem is minus del of V1 del squared of V1 r is equal to 0. So that's the Laplace's equation. We are going to make the condition, right, that V1 of r will only depend upon x and y in our coordinate system here. So we're only going to depend upon capital X of x and capital Y of y. And then we're going to write down these boundary conditions. We're going to have V1 at, so I'm recopying this one here. So I'm now recopying, so this is now V equals 0, this is now V equals 0, and we have the V naught on the 2 edges. So at y equals 0, we're going to make that equal to 0. V1 at y equals a, we're going to say that's also equal to 0. Right? And then we're going to have our symmetric boundary conditions in the x direction. And so I'm going to choose my origin to be right here. So this is actually where my origin is going to be. Okay? And so I'm going to have V1 at x equals minus a over 2 needs to be symmetric. So this is the same as V1 at x equals a over 2, which is going to be equal to, in this case, V naught with a positive sign for V1. Okay, so now I've written down the boundary conditions and the problem, and I can start the actual analysis of the problem. When I take this condition here, which is my separation of variables condition, and I plug it into the Laplace's equation, I get 2 equations out, one for x and one for y, right? And so I'm going to get second derivative of x is some constant times x. I'm going to get the same structure for y. Second derivative of y is some constant times y. and my constants are related to each other. They have to sum to 0. Cx plus cy is equal to 0. Furthermore, I can say that if I want a total non-zero solution, so the solution here is x times y. If I want a y solution that is not all 0, so if I want a total non-zero solution, I have to get sines and cosines here, and so that's going to make cy be less than 1. And so if I want non-zero solutions, cy must be less than 0. And so we're going to make this condition that cy is going to be equal to minus k squared, and cx is going to be equal to the positive k squared, where this is the same k. Moving on, we are just going to go chugging along with a problem. Whenever I now rewrite my y condition, d squared over dy squared, capital Y of y is equal to minus k squared, capital Y of y. And this gives me as a general solution, right, that capital Y of y is a linear combination of sine and cosine. So in order to find out what these coefficients are, we can start looking at applying the boundary conditions. The boundary conditions that I have that I'm going to want to apply right now are these two boundary conditions. And so boundary condition, the first one that I'm going to apply is v at y equals 0 must be 0. So whatever this x is, I'm just going to copy this x of x, I don't care about it right now, and then I'm going to plug in 0 for y. Sine of 0 is 0, and so this is a sine of 0, which is of course 0, plus b cosine of 0, and cosine of 0 is itself just 1, must equal 0. Well, this will only always be equal to 0 if we have the condition that b is equal to 0. So we'll just use that. The next boundary condition is at y equals a. This should be equal to 0 as well. So again, copying down, this is going to give whatever x is. Now b is 0, so I don't have that anymore. I'm going to have a sine of ka. This must be equal to 0. Well, if a is 0, the whole solution is 0, and again, that's not interesting, so a shouldn't be 0. X can be whatever it is, it's also not 0, so sine of ka has to be 0. This puts a condition that ka must be some integer multiple of pi. That's where the signs are 0. And so that condition translates to us that k is n pi over a, where n is an integer. And so that's the condition that we're going to go with. Now I can look at the x differential equation, capital X. Now I can plug this in, right? So this is positive n pi over a capital X of x. Now the solution to this would be exponentials, but again, because I have this nice symmetric case, I know that I'm actually really going to want the sinh and coshs. So I'm just going to write those down from the start. And so I'm going to have x will be d sinh of n pi over a x plus e cosh of n pi over a x. Now we have something that's kind of fun. We're going to say due to the symmetry, we know x must be symmetric. X must be symmetric. Since we know that d must be 0. So d has to be 0. So that's kind of a cool one that we can run right away with. And so now we can write down both what x and y are. Okay, so y of y, just copying it down, this is a sine of n pi over a y, and x of x is e cosh of n pi over a x. Now I want to combine these for our v1. So our v1 of x and y is going to be equal. I'm going to leave a little space. When I multiply these together, I can absorb the constant into the other one. So I'm going to say this is a, then cosh, x first, n pi over a x, sine of n pi over a y. And now here's something interesting. This is true for every single value of n, or for every integer value of n. This is a solution to the equation that we wrote out that has the minus del squared v1 must be equal to 0, the boundary conditions at y equals 0 and y equals a must be 0, and we have the symmetry condition that v1 at minus a over 2 must be equal to v1 at positive a over 2. So we've got 5 of those symmetry conditions guaranteed, and this is true for all n. So using the idea of superposition, the general solution then would be a sum over all possible n's like that. And that's the situation that we're sitting at right now. The final boundary condition, right? The final boundary condition that we're going to have is the v1 at r, let's say a over 2, so x equals to a over 2, must be this positive v naught. This is going to translate into our language here that sum over all possible n of a n cosh of n pi over 2, right? Because a over 2 over a, the a is canceled, so n pi over 2 times the sine of n pi over a y must be equal to some constant v naught. Well, now we have to use Fourier's trick, and so we're going to use orthogonality. So we're going to multiply by both sides by sine of m pi over a y, and we're going to integrate from 0 to a on y. And the trick that we have is that the integral dy 0 to a sine of n pi over a y sine of m pi over a y, so that's this m pi from multiplying there, is equal to 0 if n does not equal to m, is equal to a over 2 if n equals m. And so we can use this trick to help us find these a_n's. And so moving forward, we're simply going to find that when we do this trick, we're going to pick out for all of the m's that weren't equal to n, we're going to get 0. And then for the single one, when n equals m, we're going to get a over 2. So I'm just going to pick that out. I'm going to write that immediately. So am cosh of m pi over 2 times a over 2, so that's from that integral. And now I need to do this integral. So this is integral from 0 to a dy of sine of m pi over a y. But I know how to integrate sine. This is actually really a simple integral, right? This thing here is equal to minus a over m pi, and then cosine evaluated at the two endpoints. So this is cosine of m pi minus 1. Let's go ahead and put a minus and a plus, absorb that minus in there, and let's look at what this guy looks like. For m equals 1, cosine of pi is -1, so negative 1 is positive 1, plus 1 is 2, so this gives 2. For m equals 2, cosine of 2 pi is positive 1, so -1 plus 1 gives 0. And then this is just going to loop around, right? It's going to give the same thing for all of those. And so we only get a non-zero result, right, for m equals 1, 3, 5. Taking this, I can then combine everything here and solve for a. I get an is going to be equal to, I'm going to get a 2 from there, the a's are going to cancel, we get a 2 from there. So it's going to give me 4 v naught. I'm going to get an n pi, so I've switched from m here to n here. It's a dummy variable, so I'm allowed to do that. And then I have to divide both sides by this 1 over cosh of m pi over 2. Okay. So that's that. And so now I can write v1 of x and y is going to be a sum. Well, now my sum only has to have the odds. Okay. And I'm going to get a 4 v naught over n pi cosh of n pi over a x divided by cosh of n pi over 2 times sine of n pi over a y. And so that's the solution for v1. Now, in order to do the trick for v total, I just have to do this rotation, and so my v total of x and y is going to be equal to sum n equals 1, 3, 5, all the odds of 4 v naught over n pi, and then I'm going to have exactly what I have here for v1, n pi over a x divided by cosh of n pi over 2 times sine of n pi over a y minus, and then I have to do the rotation. So this is going to be cosh of n pi over a, and this will be y, but the range of x is negative a over 2 to a over 2, while the range of y is 0 to a. So this will actually be y minus a over 2 divided by the cosh of n pi over 2 times the sine n pi over a, and here we're going to have x plus a over 2. And that is your general solution. Okay. So it didn't quite fit on the page, but hey, that's what you get for planning.